weak. Weak field Zeeman effect. We already discussed that. If B is weak, that means that the external applied magnetic field is weak. It implies that B is less than the spin orbit interaction energy upon this mu B, or simply this because this is a constant term mu B. So what it gives us that
Yes, sir.
we have to consider all terms, means all interactions actually. Terms means all perturbations.
HSO is greater than AZ.
Yes, so all perturbations in Hamiltonian, and that Hamiltonian H is given by
आवाज ही नहीं आ रही है।
तो आवाज में प्रॉब्लम किस किस को आ रही है?
सर आवाज
कट आ रही है।
आपकी आवाज तो बराबर आ रही है मेरे पास। What to do? Can you hear me?
Yes sir.
Yes, sir.
Okay. H is equal to
Sir screen.
सर स्क्रीन शेयर नहीं।
sorry. The H is given by, can you see the screen?
Yes sir.
Yes, sir.
So H will be given by H naught Hz. So all the interactions will be included. And but this HFS will be dominant term.
Sir voice cutted आ रही है।
सर आवाज नहीं आ रही।
Can you hear me?
सर आवाज ही नहीं आ रही है।
अभी आ रही है?
यस सर अभी आ रहा है। जी सर।
Not properly.
कल कितने लोग यूनिवर्सिटी आ रहे हैं पहले ये बताओ।
जी सर
चार।
हमारा ग्रुप आ रहा है।
हम भी
और कोई?
No sir.
हिमांशु आवाज?
Yes sir आ
Yes,
रही
sir.
है।
Okay. So in this case, the fine structure term will be dominant as compared to Hz. Since we need to see the effect of Hz, that is the external field on the atom, that is what the Zeeman effect is. So we cannot totally ignore this term. So we have to take that term as well. So there is some contribution from the Zeeman term as well as from the hyperfine structure term. But at this time, fine structure is more dominant as compared to Zeeman effect. But we have to keep in mind that both will interact with the atom. Both will act as a perturbation to the atom. So in this case, where the Hamiltonian contains similar perturbations at the same time, So we have to treat them then individually, stating first with the most dominant, then the next, and so on. This is how we treat them. In this case, we can write then H will be equal to H naught. We know it is an unperturbed which contains a p square by 2m term plus v of r, which is e square by 4 pi epsilon naught into z. That's the potential energy term and the kinetic energy term, and that will be H naught. And this is the unperturbed energy, which you can say that is the ground state without any perturbations when we do not consider any external perturbation, including the fine structure. And there will be a fine structure which we have already determined in earlier classes, plus the Zeeman term is EB by 2MEC. That is actually, here we have J plus SZ, because we know that the Zeeman term will be EB by 2MEC into, it is LZ plus twice LZ. When we this term, I can write it as this term as it is EB by 2MEC LZ plus SZ plus SZ. This is J, this is S.
Plus S.
That is how it comes, JZ plus SZ. Now to get the eigenvalues, first order perturbation calculations. So from first order perturbations, first order perturbation calculation, the contribution of Hz is given by Ez, let it be Ez, and it is a first order. So I can write it as, in terms of eigenvalues, NLJ MJ, it is Hz, because we are in the J, we have to J this angular momentum. So it is EB by 2MEC, it is NLJ MJ, it is JZ plus SZ.
SZ. Energy.
So this is J here, MJ. I can write it as, it is EB by 2MC and LJMJ. I can write it as JZ plus
NLGMG. NLGMG. SZ.
MJ. So we can write it as, this is simply MJ h cut plus, I can write here EB by 2MEC. Here actually it is MS now. So S is coupled to J. So that is why we cannot write separately SZ here. And this SZ, actually this term, because we are then the J eigenstate, this SZ is given by that term, Wigner record term, and that is this is actually J square, J square, yes. So I have changed the orientation actually, so don't worry about it. Here it is. Now you need to calculate this j dot s. So you know that j is equal to L plus S. Okay, and I can write then it is equal to, so j dot s is equal to L plus S dot S.
L dot S plus
L dot
Okay, so I can write it as it is L
dot S.
plus S square.
dot S.
Okay, so L dot S you can calculate from this. So I can write j is equal to L plus S. So j square is equal to,
J square. L square plus S square minus 2 by L dot S.
okay. So I can write it as it is equal to L square plus S square
Plus
L
S
dot
square
S. So you
is
can
like
calculate L dot S
L
from here.
dot S.
So I can write j square minus L square
Yes.
minus S square divided by 2 is L dot S.
S.
So put it here.
J dot S.
So I can write it. So it gives j dot S is equal to L dot S. So it is j square minus L square minus S square divided by 2 plus S square here. This in this term. Can you see it?
Yes, sir.
J dot S is equal to, it is j square
S square
L
minus L
square. It is
square
2s square minus S square is
plus S square
plus S square divided
plus
by
S square
2.
by
And
2.
here is actually wait, yes,
Plus
twice it is 2. Okay, this is 2 here. Now, so we can write it as, now use this value here instead of this j dot s. So we can write then n l j m j s z is equal to, it is j square minus L square plus S square divided by 2 j into j plus 1 h cut square here. Okay, 2, yes, 2 will be there into m j h cut. Okay, because this term is m j h cut. Now use this value here. Sorry, this is incomplete here, so you can understand it. This, it is n l j m j. So it gives us this hz, yeah, en1 ez1, the first order Zeeman correction. Ez1 will be equal to eb by twice mec, this term. I will take it common. I will take it mj cut common. Here mj cut and here mj cut. This and we have here. So that is here common. And I can write then it is 1 plus it is j square minus l square plus s square divided by 2i j into j plus 1 h cut square. Okay, because mj h cut I have taken it common. Now use j equal to under root of j into j plus 1 h cut. Okay. And when you square it, so j square will be j into j plus 1 h cut square. Similarly, L square will be equal to L into L plus 1 h cut square, and S square will be equal to S into S plus 1 h cut square. Okay, so when you use these values into this, you will find that EZ1 will be equal to here.
सर आवाज नहीं आ रही है.
Can you hear me? अभी भी कट के आ रही है?
नो सर अब ठीक आ रही है.
Okay, so use this value, these values here. We will find that we will get EB divided by 2MEC MJH cut is equal to 1 plus here J into J plus 1 minus L into L plus 1 plus S into S plus 1. यहाँ से H cut square कॉमन आ जाएगा and divide by 2J into J plus 1. H cut square from here and H cut square from here,
Cancel.
that will cancel out. Okay, so I can write it as it is EB divided by here H cut is there. Sorry, H cut I have written already. I have already written that. So 2MEC it is MJH cut. Yes, MJH cut, and here I can write it as GJ. There is some, if you solve it, sorry, if you cross multiply it, so what we are left with?
3 times
Yeah,
3
it is
times
2J into 2J into J plus 1. So EB H squared divided by 2MC to 2J into J plus 1. Sorry, oh sorry, this whole is GJ. This whole land factor. This whole is land factor. 1 plus J into J plus 1 minus L into L plus 1. So this whole term, this is GJ. Don't need to multiply it. It gives us EZ1 is EB 2MEC H cut, and it is MJGJ. This is equal to B mu B MJGJ. So this is the first order energy correction for anomalous Zeeman effect, weak field case. This is a final expression, and we can modify it further to get more defined result. Like if you have L equal to 0, when L equal to 0, that's pure spin moment, there is no orbital moment, J is equal to S. At that time J will be equal to S, and we have GJ equal to that is J will be equal to half, so it is G half, because J equal to L plus, okay, so it is half L plus minus S actually, so I can write GS at that time, G half or simply GS here, it is 1 by 2. Sorry, this comes out to be 2 from this expression here, if you put it here in this expression. So GS will become 2.
Sir, 2 आएगा. Yes, sir.
Yes, I have written it 2.
2.
Okay.
Yes, sir.
And when S equal to 0, then J is equal to L. When J is equal to L, then we have GL equal to 1.
Then G.
Okay. Now, if for example, you consider a particular atomic state and you want to see what happens to the transitions at energy levels when you place in a weak this magnetic field, in the case of this Zeeman effect. So in that case, yes, please. Okay, somebody is joining late. कौन लेट आ रहा है? आवाज कट रही है? But different values of J, because J is equal to L plus minus S.
Yes.
So it gives us L is equal to J. So J has a different value. If we have L same, for example here, forget about this, let me tell you. Take this. So J is equal to L plus minus S. So S is plus half, minus half, but
Minus
J
half.
is different for same value of L.
Yes.
Okay. So it gives us different GJ values corresponding to S equal to 1 by half and S equal to minus 1 by half. Okay. Due to spin, the different values of J are not equal. And we can have then GJ equal to L plus minus 1 by half. This J equal to L plus minus 1 half is 1 plus minus 1 by 2L plus 1 when you put up the value of S. When you put up the value of J.
2G plus 1.
Okay. And I can write it as it is 2L plus 2 divided by 2L plus 1 when J is L plus half, and it is 2L upon 2L plus 1 when J is equal to L minus half. Sorry. So you have to put up J equal to L plus half and put the value of S equal to 1 half at that instance in this equation here. When J is equal to L plus half, so S is half. When J equal to L minus half, S is minus half. So both these cases need to be substituted here, and you will find this expression. This. So in this case, we see that the magnetic field splits the energy levels, the magnetic field, external magnetic field actually, it splits the energy levels into delta E equal to B mu B Gj Mg. And in the case of this normal Zeeman effect, where we have ignored the spin, there was an equal spacing. So because of this Gj here, we have an unequal spacing. Because for each term, for each energy level, the value of the Gj changes.
Gj is different.
Different.
Sir, हमने पूरा Hamiltonian निकाला.
Yes, हमने पूरा निकाला है actually. We have to
Sir,
only
लेकिन जो हमारी
we have here
वो
we
fine structure term रह गई.
fine structure we have already studied. We have already derived that separating the separate class. So what here we are
Sir,
concerned.
हमने इसमें मगर मत ऐड की है.
So that will give a separate shift.
Okay, sir.
That hyperfine structure term or the fine structure term will give it its own separate shift.
ठीक है, sir.
Similarly, the Zeeman term, the Zeeman interaction will give it its own this splitting term, the shift. So this is what we are calculating actually, the Zeeman shift. This fine structure we have already calculated, including those spin orbit, relativistic, which are the main contributors to that fine structure. And there we saw that the multiplicity was given by the 2L plus 1 in the normal Zeeman effect, but here we have 2J plus 1 in this case. And in this case, the expression which we found, so we can write the total, I will write the total energy. Let me write it here. This is ground state, unperturbed. This is fine structure first order. So I can write it this is simplest form of this. If you remember,
Yes, sir. Mg plus
MJGJ. Okay, so this is the complete expression of the energy of the atom, including all the perturbations, energy level of that atom. Okay, and here we have a mj factor. So that mj, you all know that it goes from minus j to minus j plus 1, minus j plus 2 up to 0,
through
then
0
plus
to
j.
plus j.
And the spacings between the sub levels after splitting are not same here, because j changes L minus half and L plus half. Okay, so when it changes, so we have different values of the energy level. So this is weak field, this is strong field. So what was the normal Zeeman effect, the energy shift? I will take strong field here, weak field here. What was in the case of normal field Zeeman effect? So the energy shift was B mu B.
MH cross omega L.
It was simple, yeah, MH cross omega. Yes, so it was MH cross M mu B D. Okay, so and in this strong field case, this was B mu B, and it was ML plus,
ML plus 2 MS.
and here we have it is B mu B GJ MJ, where GJ has different values. It is 12 plus 2 by 12 plus 2 by 12 plus 1 for j equal to L plus half, and it is 12 by 12 plus 1 j equal to L minus half. Here those lines, those spectral terms for which this ML plus 2 MS is same, they are degenerate, they are not non-degenerate, they have the same energy. And here the degeneration is completely lifted now here in this case, because it was independent of L. Here the degeneracy is in the L is lifted, because for same L the energies are different now, corresponding to J equal to L plus minus half in this case.
Yes, sir.
Okay. And I will give a simple energy level diagram. I hope you will understand it. If not, we can discuss it then later on, no issue. So let me show it here. Maybe it is available somewhere here. Ah, sorry, it is not here. Mm, yeah, here it is. Can you see this diagram?
Yes, sir.
Here it is. Now see here. This is 3s half term. Sorry. This is 3s half term. Gj is 2 for 3s half. So when you place it in magnetic field, this Gj will change in Mj Gj here. This is plus 1, this is minus 1. This is plus half, this minus half. And you can calculate this difference actually using that expression Mj Gj mu b Gj Mj. Okay, this is the difference. And these are 2 in the magnetic field. When you have another term 3 2p half, so Gj for this term is 2 by 3, and using that expression in the external magnetic field weak field Zeeman effect, you will see that corresponding to Gj you have 2 different values, because now the splitting will be determined by number of levels will be determined by J value, and J will be determined by L plus and half and L minus half. That is change in the spin. The spin magnetic moment vector will take part, spin magnetic moment, unlike in the case of normal Zeeman effect and in the case of strong field,
Sir,
because in strong field we ignore that, and because of the strong field case we ignored overall the interaction of the L and S. So here L and S are both combined in this Gj term. Okay, so this is for this case. And if you see the possible transitions, the selection rules are that delta L delta J plus minus 1 0
plus minus 1.
1 0. Okay, these are dipole transitions, so those selection rules will remain valid. And J equal to 0 to J dash equal to 0, that is not valid. So that is not allowed in these dipoles. Similarly, so these splittings can be calculated then. If you take simply Gj equal to 2 by 3 for this, and you place it in the magnetic field, use that expression, this expression, this. When you use that expression and put up the value of Gj here for J equal to L plus half and J equal to L minus half, you will get up that spacing. You will find that spacing here. This splitting and a 2 by 3 mu b into b. Okay. Similarly for this 3s, okay, just try it. I will send you this example as well on to the through the WhatsApp group. So just try to understand it, and if there is any issue, please let me know. Okay.
सर अगर हम वैसे करती
Yes,
थी
sir.
ना मतलब एन एल एम वो आर जैसे
ले लो,
लेते
no
थे
issue. For this case, if you take
नहीं
this,
उसको सर उसको पता था ये इक्वली स्पेस्ड है यहाँ पर मत है इक्वली स्पेस्ड
this is not equally spaced. That is the main difference between the normal and the anomalous.
GJ, yes, sir.
सर
Yeah.
yes, sir.
Okay, so that is how we differentiate normal and anomalous. Here delta E1, that is for J equal to L plus half, and delta E2 for J equal to L minus half, that is not equal.
So is this only because we add a spin here in
Yeah,
anomalous?
we take the both the LS coupling as well as the external magnetic field.
External, yes.
Okay, so that LS coupling takes part actually here. That's how the total orbital angular moment, the total magnetic or the angular moment of the atom comes into picture.
Sir, okay.
Okay, so I will leave here. If you have anything to discuss, we can discuss it in the next class.